Hello everybody, welcome to the Ultimate Physics channel. In this video we are going to solve some problems on Blackbody spectrum and Planck's law. Let us do a quick recap of the concepts involving Blackbody radiation and Planck's radiation law before we proceed on to solve some problems on the same topic. Stefan's law or Stefan-Boltzmann's law. This law gives us the total radiant power due to a black body, and that is denoted by capital R suffix T, which is equal to a constant sigma times T power 4, where T is the temperature. So here the symbol R suffix T is the radiancy or total power radiated by a black body per unit area at a temperature T, and sigma is called as the Stefan-Boltzmann's constant, which is given by the value 5.67 into 10 power minus 8 watts per meter squared per Kelvin power 4. The next important law in this topic is Wien's law or Wien's displacement law. Wien's displacement law is given by lambda max times temperature T is equal to a constant, and this constant is the Wien's constant, which has a value 2.898 into 10 power minus 3 meter Kelvin. That is a unit for the Wien's constant. So we can express this law as lambda max times T is equal to 2.898 into 10 power minus 3 meter Kelvin. Here the lambda max is the wavelength at which the energy density or the spectral intensity of a black body is maximum when the energy density is plotted as a function of wavelength lambda. So at lambda max the energy density goes to maximum. The most important law in the black body radiation is the quantum radiation law given by Max Planck, which is called as the Planck's law. Max Planck proposed his radiation law to explain the black body spectrum. The Planck's radiation law is given by, we can either write it in terms of the energy density rho of lambda comma T, since it is a function of both the wavelength and the temperature, and that is equal to 8 pi h c over lambda power 5 1 over e power h c over lambda kt minus 1. This is one way of writing the Planck's law. Of course, you could write that in terms of frequency also, but it is always more convenient to express this in terms of wavelength. And then one can write an expression for spectral, this is of course energy density, when we consider a cavity and the black body radiation is from the cavity. There is another quantity which is related to this, that is called as spectral intensity, which we denote by a symbol capital lambda, which is a function of the wavelength small lambda and the temperature T is equal to 2 pi h c squared over lambda power 5 1 over exponential hc over lambda k t minus 1. The relationship between these two quantities is simply the spectral intensity which is a function of wavelength and temperature, is equal to C over 4 times the energy density rho, which is a function of again the wavelength and temperature T. In this, h is the Planck's constant, c is the speed of light, lambda is the wavelength, k is the Boltzmann's constant, T is the temperature. In the next one, the same symbols are used, and c is of course here the velocity of light. With this information, we can proceed on to do the problems. The first problem: the surface temperature of Sun is about 5800 Kelvin and it behaves very nearly like a black body. This is obtained from the measurements of the spectral distribution of the Sun. What is the wavelength at which the peak of the solar spectrum occurs? It's a simple problem to begin with. Sun can be treated to behave very nearly like a black body and its surface temperature is about 5800 Kelvin. So what is being asked is, what is the wavelength at which the peak of the solar spectrum occurs? We know that the black body spectrum, when we plot the wavelength and the energy density, for example, or in this case you can even plot the spectral intensity, the shape of the curve is like this. Now the wavelength at which the energy density or the spectral intensity is maximum, that wavelength is lambda max, and this spectrum is recorded at a temperature T. So according to Wien's law, this product of this particular value of wavelength times the temperature, of course, is a constant which is called as the Wien's constant, whose value is 2.898 into 10 power minus 3. This constant's units are meter Kelvin. Now we have temperature information here, which is given here, and the wavelength at which the peak of the solar spectrum, is here, and that corresponding wavelength is this lambda max. That is being asked. So let us calculate that. Lambda max is therefore equal to 2.898 times 10 power minus 3 over the temperature T, and that is 2.898 into 10 power minus 3 over 5800 Kelvin. So lambda max is equal to 2.898 into 10 power minus 3 over 5.8 into 10 power 3. I'm just writing it in this way so that I can easily simplify the calculation. So this particular number, the 2.898 over 5.8, that turns out to be 0.4996, and the 10 powers are now 10 power minus 6. Now this can also be written as 499.6 nanometers. 10 power minus 6 becomes 10 power minus 9 because I am kind of multiplying this number by 1000. So my final answer is in nanometers, which is a standard convention to represent wavelengths. So the peak occurs at a wavelength of about 5000, nearly 5000 nanometers, this point, in this case. Right, let us move on to the next problem. Imagine a bright star which is at a temperature of about 20,000 Kelvin. What is the wavelength at which its energy density is maximum? Which part of the electromagnetic spectrum does this fall into? Right. So again, simple application of Wien's displacement law. Lambda max is being asked, and that is equal to the constant, Wien's constant, 2.898 times 10 power minus 3 over the wavelength, which is 20,000. Sorry, the temperature, which is 20,000 Kelvin. And this one is 2.898 over 2 into 10 power minus 7. This 20,000 I am representing it as 2 into 10 power 4, and then when that goes to the numerator becomes 10 power minus 7. So this is the remaining number that we have, which I just did a divide into 10 power minus 7 wavelengths, so meters, and this is 144.9 nanometers. So it is nearly 145 nanometers. That is the answer. Okay, let's move on to the next one. Right, so this falls in the UV, ultraviolet range of the electromagnetic spectrum. Right, so we know that typically the visible range in the EM spectrum, the electromagnetic spectrum, is from about 400 nanometers to about let's say about 750, 800 nanometers, or even 900 nanometers. So let me take it as 700 roughly, right? So this is nearly the range for visible spectrum, where the lower end of the spectrum corresponds to violet and the upper end corresponds to red. And therefore anything below that in terms of wavelength is ultraviolet. Anything above that in terms of wavelength is infrared. Of course, this naming convention is based on the frequency spectrum. So wavelength and frequency are inversely related. So in terms of wavelength, the lower wavelength is UV. So we have a wavelength that is less than this 400 nanometers, and this typically falls in the UV range of the electromagnetic spectrum. Of course, still lower wavelengths are the X-rays and the gamma rays in the electromagnetic spectrum. Right, let's move on to the third problem. Third problem: if the temperature of an object increases from 900 Kelvin to 2300 Kelvin, by what factor does the total power radiated by it per unit area increase? There is part B there. If the temperature is again brought down to 900 Kelvin, that is from 2300 Kelvin to 900 Kelvin back, what temperature is required to double the power output now? Again, this problem is an application of the Stefan-Boltzmann's law, or Stefan's law. So we know the expression for that, that is R suffix T or R as a function of t is sigma t power 4, where sigma is the Stefan's constant having the value 5.67 into 10 power minus 8 watts per meter square per Kelvin power 4. And now therefore using this one can easily calculate when the temperature is 900 Kelvin, which is the initial temperature, T is equal to 900 Kelvin. What is the R value? Right? Similarly, using this formula one can calculate. Then when temperature is 2300 Kelvin, what is the R value? Now what factor does the total power radiated per unit area increases because of this temperature change? Right? So that can be simply calculated sigma, let me call this temperature as T1 and this temperature as T2. So say T1 power 4 sigma T2 power 4. Now the power will accordingly change from R1 to R2 because of the temperature changes. Now the power increase is going to be, in this case, R1 is a lower power, so I say R2 over R1. If I take, I have T2 over T1 power 4, where the common constant is the Stefan-Boltzmann constant sigma that gets even cancelled. So it's easy to work this out directly by taking the two temperatures here. And that is 23 over 9 effectively power 4. 23 over 9 is 2.556, and this turns out to be 42.65. So this ratio, the power change ratio, is simply nearly 43 times. So when the temperature of the object changes from about 900 Kelvin to 2300 Kelvin, the power radiated is increased by about 43 times. Right? So that is the first part of that question. In the second part, if the temperature is again brought down to 900 Kelvin, what temperature is now required to double the power output? So in this case, we have to just calculate the part B. Now the temperature initially is now 900 Kelvin. Now power ratio is now R2 over R1 is 2 because it's doubling now. Right? Now what is the temperature? T2. That is the question now. So again, using the same formula here, the reduced version of the Stefan-Boltzmann's law, we can get this, right? So T2 over T1 power 4 is equal to R2 over R1 so we can work this out here in the space. T2 over T1 is therefore equal to R2 over R1 power 1 by 4, or T2 is equal to T1 times R2 over R1 power 1 by 4. T2 is equal to, this T1 is 900 Kelvin, this R2 over R1 ratio is just 2 because the power is doubling and therefore this particular number, if you work out, it is 900 times 2 power 1 by 4, turns out to be 1.1892. Therefore T2 is the required temperature for us. That is nearly 1070 Kelvin. That is the answer to this problem. Let us move on to the fourth problem. Right. Calculate the wavelengths at which the following objects radiate their maximum power. The first one is liquid helium, which is at 4.2 Kelvin. The second one is an object at room temperature, which is taken to be 293 Kelvin here. The third is a furnace at 2500 Kelvin, and the fourth is a blue star at 9000 Kelvin. So we have been given 4 different temperatures of 4 different objects, and we have been asked to calculate the wavelength at which these objects would radiate their maximum power. Again, we know clearly that this is an application of simply Wien's displacement law. So lambda max is equal to 2.898 times 10 power minus 3 over temperature T. This is a Wien's constant, obviously. We have to apply it 4 times here. The first one is simply 4.2 Kelvin. So lambda max is equal to 2.898 into 10 power minus 3 over 4.2 Kelvin. The value of the wavelength you would find out to be about 0.6 into 10 power minus 3 meters, or 0.6 millimeter. Of course, we can express this as 0.6 into 10 power minus 3 meters as well. Okay, the next one is an object at room temperature, which is 293 Kelvin. So again, if you use the same formula and work this out, (293) Kelvin is taken to be the room temperature here. We will find that it is about 9.89 micrometers. The third one is a furnace at 2500 Kelvin. That is lambda max is equal to 2.898 into 10 power minus 3 over 2500 Kelvin, and that would be around 1.159 micrometers. And then the final one is the 9000 Kelvin blue star. So in this case, lambda max is equal to 2.898 into 10 power minus 3 over 9000 Kelvin. That, if you work out, you would get about 3.22 into 10 power minus 7 meters, or 322 in terms of nanometers is 322 nanometers. Right? So let's move on to the next problem. Here, calculate the temperatures of certain objects radiating their maximum power at the following wavelength. So it is the reverse of what we have done in the previous problem. That is, calculating temperatures now, knowing the wavelengths. So the first one is again application of all the 4 applications of Wien's displacement. Now the first one is gamma ray at 1.5 into 10 power minus 14 meters. So the lambda max is known now. Lambda max is equal to 1.5 into 10 power minus 14 meter. T is required, so T is equal to 2.898 into 10 power minus 3 over lambda max according to the Wien's law. Therefore, T in this case is 2.898 into 10 power minus 3 over 1.5 into 10 power minus 14 is 1.932 into 10 power 11 Kelvin, or about 193 billion Kelvin, right? Similarly, if we work out the second one, which is X-rays, T is equal to 2.898 into 10 power minus 3 over the wavelength maximum is 1.5 nanometers lambda max. Nanometers, remember, has to have a 10 power minus 9 multiplying here. And therefore, if you work out these numbers, it is again 1.932 million Kelvin, right? Third one, temperature is for a red light of 640 nanometers. So if that is worked out, 2.898 into 10 power minus 3 over 640 into 10 power minus 9, since lambda max is in nanometers. If this is worked out, we would get about 4.528 into 10 power 3 Kelvin, or nearly 4528 Kelvin. And not finally, we have still two more to go. So D is TV broadcast waves, right? The next one, where lambda max is given to be 1 meter. So lambda max is 1 meter. We need temperature, so we simply use again Wien's law to get this. So the temperature is in millikelvin now, right? This is the answer. The next one is lambda max is equal to, that is for the AM radio waves or amplitude modulated radio waves, which is given to be 204 meters. They are large, right, waves having wavelength in the range of 200 meters here. So that is 204 meters. So T is equal to 2.898 into 10 power minus 3 over 204. If this is worked out, we would get a temperature of about 14.2 microkelvin. So an object emitting at this wavelength, its maximum power, if it is at this wavelength, then its temperature will be in microkelvin range, right? So let's move on to the next problem. Right, white dwarfs have been observed with temperatures as high as 200,000 Kelvin surface temperatures. What is the wavelength at which such a white dwarf would radiate its maximum power? Similarly, again, application of Wien's law here. Lambda max is being asked, so we have to just use this formula. Right, and that is going to be about 1.449 into 10 power minus 3. This is going to be 10 power 5 in the denominator, so goes to the numerator as minus 5, so it is 10 power minus 8 meters, or this can be also expressed as 14.5 roughly nanometers. Right, let's move on to the next problem. The tungsten filament in a 40-watt incandescent bulb is at 3300 Kelvin. What are the wavelength and the frequency at which this bulb is radiating its peak power? If the frequency is assumed to be the photon frequency, how many photons does the bulb radiate per second? The third part, assuming a diameter of 5 mm for the pupil of our eye, how many photons enter our eye at a distance of 5 meters from the bulb? So we can see that there is a tungsten filamented bulb, right? And this is radiating. Incandescent bulb, this one is. So its temperature, the tungsten filament temperature is 3300 Kelvin inside this bulb. The first part is simply a wavelength and frequency problem. So it is lambda max we have to first calculate using the Wien's law. So I'm simply writing 2.898 into 10 power minus 3, which is Wien's constant over the temperature that is given here, that is 3300 Kelvin. And that, if we work out, we would find that it is about 2.898 over 3.3 times 10 power minus 6 meters, and that is equal to 878.2 nanometers. Now we need frequency also in the first part, so let me call that as nu max, which is the frequency at which the bulb is radiating its maximum power. That is going to be the velocity of light or speed of light c over the wavelength, because we know that the speed of light is merely a product of the frequency and wavelength. So we want here frequency, so nu is c over lambda. So we have to use this here. So 3 into 10 power 8 is the speed of light I am taking it to be roughly over this lambda max that we have calculated, which is 878.2 times 10 power minus 9. So if you work this out, you would find that that is equal to 3.416 times 10 power 14 hertz, right? That's the second part of this first question here. The next question is, if the frequency is assumed to be the photon frequency, how many photons does the bulb radiate per second? Now the power of the bulb is given to be 40 watt. So if the frequency nu max, which is we have calculated to be 3.416 into 10 power 14 hertz, is assumed to be a photon frequency, then the photon energy E is equal to h, which is Planck's constant, nu, right? So the energy is, we can calculate the photon energy as because here nu is nu max actually, but that is taken to be photon energy nu, photon frequency nu. So photon energy is equal to h times nu, which is 6.63 into 10 power minus 34 Planck's constant times the frequency that we have calculated, 3.416 into 10 power 14 hertz. So if this is worked out, we will get 2.27 into 10 power 19 joules energy, right? So that is what we are getting. Now this is the energy of a photon that the bulb is emitting. Now the total energy of the bulb in terms of the power is given as 40 watt. That means the bulb is emitting about 40 joules every second. Sorry, this is minus, right? So here it's minus 40 joules. So the number of photons can be calculated, number of photons that the bulb is emitting per second, obviously, because we have the power of the bulb given as 40 watt here, which is 40 joules per second. So number of photons per second is directly calculated as the total energy, which is 40 joules emitted per second, over the energy of a photon, which is 2.27 into 10 power minus 19. Right? This turns out to be 1.766 into 10 power 20 photons every second, number of photons per second. Right? So the part B is answered. How many photons does the bulb radiate per second? That number is this 1.766 into 10 power 20 photons every second. The third part of that is, assuming a diameter of about 5 millimeter of the pupil of our eye, how many photons enter our eye at a distance of 5 meters from the bulb? So from this bulb, the filament and emitting this way, human eye is at about 5 meters here, right, from this bulb. This distance is 5 meters. If that is the case, and the pupil of our eye is 5 mm area, right, there's a size of 5 mm. Now what is asked in this part is, how many photons enter our eye at a distance of 5 meters from the bulb, right? So here we can simply see that the number of photons per unit area we have to first calculate, and that area is a sphere. Here you can see that at this point this bulb radiates right equally in all directions. So we have a 5 meter radius sphere of 5 meters. So this is effectively the area where we are talking about the surface area of a sphere that is emitting a certain number of photons per unit area that we have to calculate every second. So if you do that, what we can write down here is, let's say, the power per unit area radiated at 5 meters, right? That is equal to the number of photons. Sorry, we don't even need power per unit area. We need number of photons per unit area only. So we say that number of photons per unit area at 5 meters, right? That is equal to the number of photons, total number of photons emitted by the bulb is 1.766 into 10 power 20 photons over the area that we are talking about is a spherical area. So the area of the surface of that spherical area is 4 pi r squared, where r is the radius, which is 5 meters here. So 4 pi, this r is 5 meters, so 5 squared we do. So this turns out to be 1.766 into 10 power 20 over 25 times 4 is 100, so 100 pi in the denominator here. That is the number of photons per unit area. So we say photons per meter squared. Now how many are being received by the eye, that is a pupil of the eye, at this particular point on the surface of this large sphere? And that depends on the area of the pupil of the eye, and the size is given as 5 mm here. That is the entire size of the no, the eye itself, the pupil, right? This is the size of the pupil. That is 5 mm. So the area of the pupil can be calculated as it's a circular area, right, pupil, and that is pi r pupil, let's say rp squared, that is 3 point, let's keep it as pi, what is it, pi times 5 mm is 2.5 radius, because 5 mm is the size of this thing. 5 mm is given as size of the pupil, so we can see that it is 2.5 mm. So I am writing it is 10 power minus 3 meters. In meters it is 10 power minus 3 to be multiplied, and square of this. Now the number of photons that are therefore received by the pupil, or number of photons reaching the eye, at that point is equal to number of photons per unit area emitted by the bulb, which is 1.766 into 10 power 20 over 100 pi times pi into this one, 6.25 into 10 power minus 6. So here straight away we can see that these two things cancel out, and then this 100 is 10 power 2, so if we cancel this out we have 10 power 18, and then this cancels this 10 power minus 6 and becomes 10 power 12 on the numerator. And then if we multiply these two things, if we multiply, you would get the number that is required for this. So that is 1.766 times 6.25. That is 11.038 into 10 power 12 photons. That is the number of photons that are reaching the eye. Have we missed out anything? Right? So right, so this is the number, so we can also write this as 1.11 or 108 or 104 rather, let's say 104, right, into 10 power 30 photons. That is also fine. That is the answer to this question, the number of photons reaching the eye. The next problem, the energy from the sun at the top of the Earth's atmosphere is 1.36 into 10 power 3 watts per meter square. Assume the Earth behaves like a black body at uniform temperature. What is the equilibrium temperature of the Earth? So we have sun emitting radiation like a black body. It's nearly a black body. Earth is somewhere here, right? And then it is receiving radiation from the sun. At some distance it's there, and then of course there is a thin layer of atmosphere on the Earth, and at this point the energy is given to be in terms of power 1.36 into 10 power 3 watts per meter squared, which is the solar constant at this point. On top of the Earth's atmosphere. Now assuming that the Earth behaves like a black body, that is, it is absorbing all radiation incident from the sun, What would be the equilibrium temperature of the Earth? That is a question here, right? So first, how much energy Earth is absorbing of this particular energy that is arriving at this top of the Earth's atmosphere, that is 1.36 into 10 power 3 watts per meter square is the power. So first let's calculate the absorbed power. Right? So let me do that here. Power absorbed. That is equal to 1.36 into 10 power 3 times the radius of the Earth, because it is behaving like a black body, and it's, let's say the radius of the Earth is RE. The area over which Earth receives from the Sun is like a circular area of radius, Earth's radius RE, right, this point. And therefore I multiply simply by its area of the circle there, that is pi times r e, the radius squared, pi r squared. And then the power emitted by Earth is whatever the total power per unit area that it emits, that should be multiplied by the surface area of the Earth. The surface area of the Earth is the entire surface area through which it starts emitting the radiation like a black body. So that is surface area is 4 pi r squared, so 4 pi r e squared. So while receiving, it receives radiation from the Sun over a circular area, because Sun is going to see a circle, Earth as a circle, and Sun is emitting radiation onto the circular area. So I am taking pi r squared on the numerator, on the first part, absorbed part. But here for the emitted part, it is emitting through the entire body, that is, it is taking radiation from the Sun over an area, and then the entire object's surface is emitting radiation. And therefore here the additional factor 4 for the surface area of a sphere. On top here it is surface, the area of a circle. That is the difference between these two. Now, assuming that it is a perfect black body, if it has taken amount of radiation from the Sun, it has to emit all the radiation. So these two must be equated, right? Therefore, the power absorbed is equal to the power emitted. So if we equate these two things, right, we see that the pi and this pi will cancel over, right? And what we would have is capital R is equal to, of course these two also would cancel, right? So we have R times 4 here, right? So 4R would be equal to this number, 1.36 into 10 power 3. So I have merely equated these two here, and therefore doing the simplification. So R is equal to, that is the total power radiated per unit area, is 1.36 into 10 power 3 over 4, right? That is equal to, according to Stefan's law, sigma times T power 4, because we need temperature here, right? The temperature at which this is happening. So we are trying to get to that now. So the temperature T power 4 is equal to 1.36 into 10 power 3 over 4 times this sigma goes to the denominator, so sigma. and 1.36 into 10 power 3 over 4 times sigma is Stefan's constant, so 5.67 into 10 power minus 8 is a value, and therefore they can be this can be simplified. We would get, if you do that math, 59.96 times 10 power 8. So T is equal to 59.96 power 1 by 4 times 10 power 8 power 1 by 4 becomes 10 power 2. So if this is worked out, we would get a temperature of nearly about 5 degrees centigrade, or 278.3, let's say, Kelvin. So this is the temperature if of the Earth, if Earth behaves like a black body. Right. So let's move on to the next problem. At what wavelength does the human body at 37 degrees centigrade radiate? What would be the total power radiated by a person of medium build with height of 175 centimeter and 13 centimeter radius approximating to a cylindrical area? So here a human body is approximated to a cylinder, and that's radiating like a black body, right? That is the assumption that is given here. And we are asked to calculate the total power radiated by a person of medium build, where the height is given to be about 175 centimeter, and then 30 centimeter is the radius of such a cylinder, right? If this is assumed to be a cylinder, 13 centimeters, right? And temperature of this person is given in centigrades as 37 degrees centigrade. So lambda max is equal to 2.898 into 10 power minus 3 over the temperature, which is 37 degrees centigrade, which is approximately 310 Kelvin. Right, so we are adding into, for the Kelvin scale, the Celsius scale is 37, we are adding 273 to it roughly, so nearly that is 310 Kelvin, right? So lambda max, if we calculate the wavelength at which this person is radiating, that would be 2.898 over 310, that would be 9.35 into 10 power minus 6 meters, or about 9350 nanometers lambda max. So this is clearly in the IR range, right? Infrared of the electromagnetic spectrum. So that is a wavelength at which the human body radiates if it is at a temperature of 37 degrees centigrade. And what would be the total power radiated by the person of medium build, whose sizes are given here? We know that according to Stefan's law, the power radiated per unit area is sigma T power 4, because here the units are watts per meter square. So if this is the case, total power radiated, how much it is? Total power is the power radiated per unit area, which is R times the area, right? Therefore sigma T power 4 times the area of a cylinder here, right? So it has 2 pi r squares over the top and the bottom, and then the curved surface area is 2 pi r h. So we have a 2 pi r h plus 2 pi r squared, right? So if we work out the numbers, let me do that, right? So power is equal to 5.67 into 10 power minus 8 for sigma here, times the temperature 310 power 4 times 2 into the radius, sorry, pi 3.142 times the radius here is 13 centimeters. So 13 into 10 power minus 2 times the height 175 centimeter into 10 power minus 2 in meters. I'm taking this, of course. So plus this bracket is for the entire thing. So plus 2 into 3.142 times 13 into 10 power minus 2 whole square. The radius is 13 centimeters. That's why. So if you calculate this power, it turns out to be 804 watts of power. The cosmic microwave background radiation, which is a relic from the Big Bang, right? So it's a Big Bang relic radiation, has a typical blackbody spectrum whose temperature is 2.7 Kelvin. So the measurements show that the relic radiation has a typical spectrum of a blackbody at temperature 2.7 Kelvin. What is the wavelength and frequency in which the intensity of this radiation is maximum? That is the lambda max, and the nu max, corresponding nu max also we can calculate. How much is the total power incident on Earth from this background radiation? So it is uniform, isotropic in all directions, and Earth is receiving this radiation. And how much is the power of that radiation? That is a question here, right? So the first part, that is what is the wavelength and frequency, is a mere application of the Wien's displacement law. So there we have lambda max, let's say, as 2.898 into 10 power minus 3 over the temperature T, which is here 2.7 Kelvin. If this is worked out, we are getting 1.073 into 10 power minus 3 meters, right? And that is about 1.073 millimeter. So it's a millimeter wave, right? Now what is the corresponding frequency for this? That is nu max is C over lambda max. So 3 into 10 power 8 I'm taking to be the speed of light over this 1.073 into 10 power minus 3 as the wavelength. This is worked out, it would be 2.796 10 power 11 hertz. That is the frequency at which we get the cosmic microwave background radiation. Now total power is the next part, right? How much is the total power incident on Earth from the background radiation? That is given by the Earth is receiving over an area, right? That is its surface area, which is 4 pi RE, RE is the radius of this thing, Earth, so 4 pi RE squared. Now therefore the total power is equal to the power radiated per unit area, which is given by Stefan's law, times the area. We know that from Stefan's law this R is sigma T power 4, and therefore we have again here sigma times T power 4 times 4 pi radius of the Earth square. Radius of the Earth RE is taken to be roughly 6.38 into 10 power 6 meters. So we have to plug in these numbers here. So sigma is 5.67 into 10 power minus 8 times the temperature is 2.7 Kelvin times power 4 multiplied by 4 times, let's say, 3.142 for pi into 6.38 times 10 power 6 whole squared is RE squared. Radius is squared here. That would be total power that Earth receives from this radiation, and that is calculated to be 1.54 into 10 power 9 watt. Right, nearly 1.5 billion watts. Next problem, if the absolute temperature of a black body is doubled, what is the factor by which its total power radiated increases? Let's say for a given temperature, the total power radiated is given by Stefan's law, right? Now, if the temperature is doubled, the total power changes, let's say, to R2, then that would be this. Temperature is doubled, so T2 is 2 times T1. That is a relationship that is given here. So in this equation, if you plug in that, R2 would be equal to sigma 2 T1 power 4. That would be sigma times 16, 2 power 4 is 16 times T1 power 4. So if you compare these two, R1 and R2, we can clearly see that R2 is 16 times R1. So the answer to the question is by how many times the total power, or by what factor the total power radiated increases if the absolute temperature is doubled, is by a factor of 16. That is, the total power radiated increases by a factor of 16. Let's move on to the next one. What is the average energy E bar per mode of oscillation for a long wavelength lambda of this, for a short wavelength lambda of this? Compare these energy values with the classically obtained value of kT. Now this is an application of the Planck's law, right? Planck's law tells us that the average energy, in the derivation of Planck's law, we get energy density. But in order to calculate the energy density, we do two things. First, we calculate the number of modes in the cavity, then multiply it by the average energy per entity in the cavity. That is this E bar. That is simply given by E over exponential E over kT minus 1. Right. If classically obtained value is kT, that is classically obtained average energy is kT. Let's do that. If the energy is kT, let's say, what would be the average energy? That also we can do, right? So first let's do for that, let's say if E is equal to kT, what would be the average energy? That is another question that we can ask, right? That is not part of this question, but just to get an idea as to, because here all this is in terms of wavelength, which we will convert to frequency, energy actually, right? Equivalent energies we will see. So let me directly take energy here. If E is equal to kT, we know that E is equal to hc by lambda, and we are taking that to be equal to kT. Therefore, lambda is hc over kT, right? If this is the lambda in the first stage, if lambda is equal to hc over kT, what would be the average energy E, which is E over exponential E over kT minus 1, which is kT over e power 1 minus 1, which is equal to, so this would be kT over e power 1 is 2.718 minus 1, right? So that be kT over 1.718. So that would be 0.582 kT. So this would be the average energy. So the average energy would be about 0.582 kT if the total energy E is kT. Now here, for comparison, we have done this actually. The actual question does not involve this calculation. The actual question is two other wavelengths or two other energy values correspondingly. That is, lambda is equal to 10 hc kT and lambda is equal to 0.1 hc kT. So because of for comparison we have done this, we will continue to do now this thing. The first case is A is equal to lambda 10 hc over kT. So 10 hc over kT. That means the energy is equal to hc over lambda, right? So hc over 10 hc times kT. Now we can clearly see that here hc and hc can be cancelled. Effectively we have kT over 10. This is the energy to be taken now for the calculation. So the average energy is equal to, therefore, E, capital E, exponential E over kT minus 1, which is equal to kT times 10 exponential 1 over 10 minus 1, which is kT over 10 times e power 0.1 minus 1, right? So kT time kT over 10 times e power 0.1 is 1.105 minus 1, and that is 0.105 times 10 is again 1.05. So we have kT over 1.05, and therefore 1 over 1.05 is 0.952. So we effectively get 0.952 kT as the average energy if the wavelength is a long wavelength, which is 10 times hc over kT. This is for comparison. We can see that if the wavelength in the previous page, we have done that calculation. If the wavelength is hc over kT, we are getting the average energy like this. And if the wavelength is 10 times, which is long wavelength, then we get average energy like this. Similarly, if we proceed on to get for the short wavelength, which is given as lambda is equal to 0.1 Hc over kT. Then we can calculate the energy to be kT by 0.1 or 10 kT energy, right? So if you substitute that here in this average energy would be 10 kT e power 10 minus 1, right? So if this is worked out, we would get 4.54 into 10 power minus 4 kT. So see that for shorter wavelengths, the average energy is too low compared to kT. For longer wavelengths, the average energy is comparable to kT. And for medium wavelengths, which we calculated on our own here, the average energy is half of kT nearly, right? So we can understand this. Right, next problem. A cavity is radiating its maximum power at a wavelength of 27 micrometer. The temperature is changed so that the cavity now radiates double its power. What is its new temperature? What is the wavelength at which it emits the maximum power now? So here a maximum power of a cavity is given, right? The maximum power of a cavity. No, maximum power is not given. The wavelength is given here, right? The wavelength is lambda max, at which maximum power is emitted. That is 27 micrometers. Now temperature is changed, right? Temperature is changed so that the cavity now radiates to double its total power. What is the new temperature? So it's very simple. We have already done similar problems in this video. So first let's calculate the temperature, right? We can say that the temperature, original temperature is T old, let's say. The new temperature is T new. According to Stefan's law, if you take the total power radiated per unit area, this is the expression, right? So in this one, if you do a ratio of T new here to the T old, let's say power 4, that is power radiated. It is going to give on the right hand side, and that is double the power, right? Double its power, so it is going to be 2 the ratio. So we need a T new power 4, let's say, is equal to T old power 4 times 2, or we need T new alone. That would be 2 power 1 by 4 T old power 1 by 4, which is 1.189 times T old power 1 by 4. What is the T old power 1 by 4 here? We have to calculate that. We haven't done that, right? So that is based on this wavelength. We can calculate using Wien's law, right? So let me do that now. Lambda max is equal to 27 micrometers, or 27 into 10 power minus 6 meters. Therefore, the temperature is equal to 2.898 into 10 power minus 3 over 27 into 10 power minus 6. That is, if you work this out, 107.3 Kelvin. And this is our T volt now, right? So T volt is equal to 107.3 Kelvin. So T new we need from the previous page. You can see that is 1.189 times T old power 1 by 4. That is 1.189 times 107.3 power 1 by 4. If this is worked out, we would get 127.6 Kelvin for T new. So that's the answer we need. Let's move to the next one. Show that RT is equal to sigma times T power 4, or prove Stefan's law using Planck's radius. So we have to prove Stefan's law or Stefan-Boltzmann's law from Planck's law, right? So we know that the Planck's law or Planck's expression for the energy density is rho of lambda at a temperature T. So let's say it's a function of T as well, is equal to 8 pi hc over lambda power 5 1 over e power hc over kt minus 1. Of course, Planck's law can also be expressed in terms of spectral intensity. This is energy density. In terms of spectral intensity, we have seen already that, let me use capital lambda for that, which is a function of wavelength of small lambda and t, is c by 4 rather times rho. That if you do 2 pi h c squared over lambda power 5 1 over e power hc over lambda kt minus 1. Here also lambda, right? So now the power radiated, right, can be calculated total power over all wavelengths, that is 0 to infinity, integration of this thing, right? That's lambda, right? T lambda. So therefore RT is equal to, let me take this expression and do it. So 2 pi h c square is a constant, integral between 0 to infinity of 1 over lambda power 5 times 1 over e power hc over lambda kt minus 1 d lambda, right? Now if we assume, in this case, let us take that, let this particular term, right, in the denominator here, that is let x is equal to hc over lambda kt. If we take that, then we can write straight away dx over d lambda. Differentiation of this is going to be minus hc over kt 1 over lambda square. Then we can write d lambda as minus kt over hc lambda squared dx, right? And then based on this we can write lambda squared, or first lambda let's write, right? Lambda is hc over kt 1 over x, and then based on this we write lambda squared hc over kt 1 over x squared, right? These are the things that we would need for substituting back into this equation, all that is required. So we are trying to convert the integration from the variable lambda to x. In order to do that, we have to do the substitution so that our integral will be arriving at in the form of a standard integral. instead of lambdas we would get in terms of x and try to easily simplify and solve it, right? So that is the whole idea. So if you do these substitutions back into this equation, let me write it here. RT is equal to minus 2 pi h c squared. Please remember this minus is a result of the minus that we are getting here in terms of conversion, right? When you do that, 1 over lambda is no differentiation, 1 over lambda squared with a negative sign. That negative sign comes up there. And then we have to integrate between infinity to 0 here in this case, because in the original integral we have 0 to infinity limits, but here we are swapping the limits or changing the limits simply because the x and the lambda are inversely related. So we want to convert from the variable lambda to variable x in the integration, and therefore this limit swapping causes the negative sign. There is a limit swapping, and then later on this negative sign therefore can be again changed to positive sign by again changing these limits from 0 to infinity. So right now, simply because of the variable change, we have a limit change as infinity to 0. And then we have, if you substitute those numbers in the previous expression, we would see that we have a kt over hc power 5 and then x power 5 dx variable has been converted, ex minus 1, and then we have a kt hc and then another hc kt squared, and then of course 1 over x squared. Now further simplification of these things can be done, right? And if we do that, and then again of course swap the limits from 0 to infinity back, we have plus 2 pi hc squared integral 0 to infinity now, simply kt over hc power 4 and x cube e power x minus 1, because here x power 5 there is a denominator x squared here, that will become x cube here, and then this thing is here. Remaining things we have kind of simplified here, and the integration variable is dx here, right? Now this particular integral alone is a standard integral, and the remaining things are constant, so you can take it out. That integration, that is 0 to infinity of x cube over e power x minus 1 dx is pi power 4 over 15. That is the value of that particular integral. So if we take that, 2 pi h c squared times kt over hc power 4 times pi power 4 over 15. So remaining things are all constants, that is 2 pi hc squared k power 4 from this bracket over, in the denominator we have h power 4 c power 4. Of course there is another pi power 4, so pi 5, and then there is a 15, that 15 comes here, and then you have t power 4 alone in the bracket, that comes out as t power 4. And then of course this can be further simplified because there is a h and h power 4 here, so I write it as 2 pi power 5 k power 4 over 15 h cube c squared t power 4. This is the total power r, and this is equal to r is equal to, this whole thing is our, if you calculate this, would be sigma. So sigma t power 4. So if you plug in these constants, pi, k, Boltzmann constant 1.38 into 10 power minus 23, all these numbers, you would end up getting sigma as 5.67 into 10 power minus 8. That's the value you would get, and therefore, of course, with units. So that is the Stefan's law, or the Stefan-Boltzmann law. Right, that we are supposed to derive. Right, let's move on to the next one. Derive the Wien's displacement law from Planck's law and obtain Wien's constant. Right, so again we have to start from Planck's law and try to derive the Wien's displacement law. We know that beforehand, let's say lambda max times t is a constant, which is the Wien's constant, meter Kelvin. So this is the Wien's law that we are supposed to know, derived from Planck's law, right? So let's start from Planck's law. Rho lambda is equal to 8 pi hc over lambda power 5 1 over e power hc over lambda kt minus 1. This is the Planck's law in terms of energy density, right? We can simply use this and try to derive Wien's law from this. Now we know that from the Blackbody spectrum, the energy density when plotted as a function of wavelength on the x-axis and energy density on the y-axis, we get lambda max, that is a maximum energy density at a particular wavelength, and that wavelength is called as the lambda max here in Wien's displacement law. Right, this particular value is lambda max. So in order to get the maximum of this function rho, which occurs at this point, the corresponding lambda can be obtained by taking this rho and differentiating it with respect to lambda and setting that differential d rho over d lambda to be equal to 0. So when d rho over d lambda becomes equal to 0, we get the maximum of the function rho, and the corresponding wavelength is lambda max, right? So this has to be done now. Of course, in this expression, we have to, let's say we assume this particular constant is, let's say, a is equal to 8 pi hc, let's take, and then in the denominator we have hc over lambda kt, right? In this, let's take b is equal to hc over kt. If we take these two substitutions and put them back in this equation, we get the rho lambda to be equal to a over lambda power 5 1 over e power b over lambda minus 1, right? And then this can be further written as rho of lambda is equal to a lambda power minus 5, right, by taking this to the numerator, and then e b over lambda minus 1. Let's take this and then proceed further. Right, now this can be differentiated and set to 0. That implies, if we do that, we have rho already as a lambda power minus 5 over e power b over lambda minus 1, right? This has to be now differentiated. We can use this formula simply, that is d over dx of u by v is equal to v times du minus u times dv over v square, right? This is the general formula for differentiation of u over v. Here u is therefore lambda power minus 5, let's say, and v is e power b lambda minus 1. A is the constant that can be taken outside of the brackets. So we can say that taking all this into account, d rho over d lambda is equal to A times the differentiation of the first thing, right? U over V. So V is E B lambda minus 1. So we write E B over lambda minus 1 times differentiation of U du. So that is this. That is minus 5 times lambda power minus 6 minus U, which is lambda power minus 5 times dv. dv is differential of this, that is e power b over lambda, and then differential of this b over lambda is minus b over lambda squared, right? And then the denominator has to be a v squared, which is this thing, e b over lambda minus 1 whole square, right? So that is the expression that we have now. Let's further go down to simplify this, right? A times of course here this minus and this minus, they would become plus, so this term can be brought as the first term, right? Now this thing, so let's do that. And then this term has a negative sign here, so this can be taken out to be at the second term. So first term, if we take this one as, then we have this lambda squared, let's say it is taken to the numerator here, that will become lambda power minus 5 minus 1, that is lambda power minus 6. And then here we are left with only b over lambda then. And this minus and minus cancels out to be plus. So we have b over lambda here, this term, second term, which we are writing first here. Then we have a lambda power minus 6. Then we have, of course, e power b over lambda. Why we are doing this? Because this whole thing is a positive. Then the minus sign in the first term can be put here, and it has a lambda power minus 6. Here it has lambda power minus 5. So to make it minus 6, we are taking one of the lambdas from the lambda squared to the numerator to make it minus 6. That adjustment we do, we can easily simplify this. So second term automatically is here from this here. So 5 lambda power minus 6 we have, and then we have e power b over lambda minus 1. So that is this term. This term goes here. This term has been simplified and brought here, right, to make things easy for us. And then of course the denominator remains the same, right? What is the denominator? That is e power b over lambda minus 1 whole square, right? If this is further simplified by dividing each term here, the first term by this and the second term by this, we have d rho over d lambda, which is equal to A times, right? Let's say we take this lambda power minus 6, which is common to both outside as well as this one outside. So we have let me use green here, right? A lambda power minus 6 over e power b over lambda minus 1 whole square. That leaves the first term here with a b over lambda, e power b over lambda only, minus the second one will have a 5, and since there is only here this one term, the second term would be e power b over lambda. We have taken no if you divide it first, you will have 1 in the denominator. So if you take it out, you have 1 again in the numerator. That is this thing, e power b lambda minus 1 comes to the numerator again, because first if you divide this alone, here there is a square, there is one term, so you have a denominator here, but when you take square out here, that term should come on this. Now this I will continue next from this expression onwards, right? So there are two things here we have to consider. We can simplify this further. Now if we expand this, we can see that either this term can be 0, because we want to equate this to 0, right? The differential, to get the maximum of the function. So either this term can be 0 or this term can be 0. But if you make this term 0, we are not going to achieve anything by that, right? So the second term alone can be 0. That condition we will take and try to proceed further. So the second term alone is b over lambda, e power b over lambda minus 5 e power b over lambda minus 1. Whole thing is 0. If you take that, then if you multiply the whole thing by e power minus b over lambda, then we have b over lambda minus 5 1 minus e power minus b over lambda. The simple adjustment if we do, right? Then we can multiply whole thing by lambda now to make it more simple. Then we have b is equal to 5 lambda 1 minus e power minus b over lambda as the final expression for b, which involves b lambda and b over lambda, right? This expression can be solved by a guess. So first what we will do, two things we can do. First is we can make a guess value, guess a value for this b over lambda. So start with a guess and then substitute that, calculate b over lambda based on that. Then substitute back into the equation for b, equation for b. If you do that iteratively means that you have to do it for a repeated number of times to arrive at a nearly identical value. And nearly identical values if you get for b over lambda, that means you have arrived at the solution, right? So we can do that here. If we first, let's say, take a let me show that calculation here, this place. First, if let's say I start with a guess value, b over lambda, let me start with 5, right? If I substitute here in this equation b over lambda as 5, I would get p is equal to 5 lambda times 1 minus e power minus 5, right? p is equal to 5 lambda times 1 minus this would be 6.738 times 10 power minus 3. 1 minus that answer, if you do, you get 0.99. So 5 lambda times 0.9933 b. Again, you can do the b over lambda here. From here you can calculate, that is 5 times this value, that is 0.9933. that would be 4.9663, right? So So that is our first b over lambda that we have calculated. Starting from a guess of 5 b over lambda, we have arrived at a lower value 4.9663. Now we can further substitute this value back into the original equation for b here. Now therefore b is equal to 5 lambda 1 minus e power minus, instead of 5 here, now we will do 4.9663. This is the substitution iteratively. We are doing substitution iteratively from starting from a guess of 5, we are getting 4.9. If you do this particular thing, we would get the next value to be lesser, right? So that would be, let me just check that. Yeah, if you do that, 4.9663. Yeah, now you would get b is equal to 5 lambda times 1 minus 6.9688 or 9 into 10 power minus 3. Now if you do this, you get 5 lambda 0.9930 b. So b over lambda is 5 times this number. That would be 4.9651. And if you again substitute this value back into the original equation to arrive at another b over lambda, you would find that now b over lambda is, for 4 decimals if I take, that is kind of stabilizing to the same value now. Since that has stabilized to the same value of 4.9651, I can take that to be a reasonably good approximation for b over lambda. So in the original equation, in the previous pages, if you check, yeah, I have taken b to be hc over kt. So I can finally solve it here. For lack of space here, I'm doing, let's say, that I got b over lambda to be, the last page, 4 point, a reasonable guess I got 9651, right? And that value does not change much up to at least 4 decimals I'm taking. So you could take as high accuracy as you want, as good an accuracy you want. You can take 7th decimal or 8th decimal, so you would get much better accuracy. But for the sake of the method, I'm just explaining only up to 4 decimals here. If up to 4th decimal you are satisfied with accuracy, you can take this, and then b is hc over kt. So you have hc over lambda kt, if you compare these two, as 4.9651. so if you retain the lambda t in the denominator here to numerator here and rearrange this equation, you would get hc over k times 4 point this value 9651. Now that is your what? This lambda is the lambda max, simply because we have done a differential of d rho over d lambda to get the maximum value of rho, and that occurs at a point that is lambda max. So lambda max times t is this Wien's constant, 2.898 into 10 power minus 3. So you are arriving at Wien's law starting from Planck's law here. So that has been asked in the question. Derive Wien's displacement law from Planck's law and obtain Wien's constant. So Wien's constant is the value of this term. H is 6.63 into 10 power minus 34. You can take C is 3 into 10 power 8. K is 1.38 into 10 power minus 23. Boltzmann's constant. So if you substitute these constants here and this number, that you got by doing the guess iteration method, you would get this particular number value for Wien's constant. So we have derived not only just Wien's law, we are also getting the value of the Wien's constant, thereby solving this problem, right? So that brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.